Let's take a look at the Dirac delta function. The Dirac delta function is defined to be, we're going to give it a variable delta of x. It's going to be infinitely high when x is equal to 0 and very, very narrow. So this is x equal to 0. So it's defined as delta of x 0 if x equal to 0 and infinity if x equal to 0. I'm sorry, it's 0 if x is not equal to 0. So it's 0 everywhere, but at x equal to 0 it's gonna equal to infinity. And the reason why we study these functions, because they give us two states, the bound states and the scattering states. As you know that the harmonic oscillator, it's a bound state. It oscillates between 2 points. But the free particle is a scattering state. So in this example, we're gonna take a look at this function that have both in it. So with this given, we have to say a few things, that if you multiply a function f of x times the delta function x minus a, this is gonna equal to f of a. Think of it. So we have a function f of x times this delta function of x minus a. So it's gonna be equal to, it's gonna give 0. It's gonna kill this f of x anywhere but when f is at point a. It's gonna give us that value. So that's one thing we have to keep in mind. I gotta put examples for this one here at the top right corner. 2, if you integrate this delta function from negative infinity to infinity, delta of x dx, this must equal to 1, right? So now if we integrate the integral from negative infinity to infinity of any function f of x times delta of x minus a dx, this is gonna give us f of a times the integral from negative infinity to infinity of delta x minus a dx, and that's just 1, so this integral is equal to f of a, right? So now let's look at our potential. So now our potential function v of x is going to equal to some constant minus alpha times the delta function f of x. If you're going to say y minus alpha, it's just to make the dimension works, because v is energy, right? It's potential energy. But if you look at the delta function, it has units of dx equal to 1, right? So this, our delta function is 1 over length, right? So this alpha has to be with units joules times length. That's what this alpha is doing here. So with this potential function, our Schrodinger equation reads minus h bar square over 2m times the second derivative of psi with respect to x minus alpha delta of x times psi equals e times psi, right? So this equation yields both bound states, so bound states where the energy is negative, and scattering states. Where the energy is positive. Think of these bound states and energy scattering states if you look at just statistical mechanics in one-dimensional problem. So this is the bound state, this is like, let's say this is the potential, and we have our car over here, and the energy of the car is not big enough to overcome this potential energy here. On the other hand, the scattering state looks something like that, and let's say we have our car here. The energy of the car is greater than the energy of this potential, so it's gonna scatter, it's gonna go through here and come down. So that's what I mean by bound states and scattering states. This equation here, the Schrodinger equation, it has both in it. So our job now is to solve this equation. As usual, we're gonna give new variable some name, so let's define the new variable k to be minus 2m times e divided by h bar. So with this in hand, the Schrodinger equation reads, after we move things around, we have the second derivative of psi with respect to x equal to minus 2m times e divided by h bar square times psi, times psi, which is the same as the second derivative is equal to k squared times psi. Does this equation look familiar? Of course it does, and we know the solution for it. So the solution for this equation is psi of x equals to some constant a times e to the minus k times x plus some constant b times e to the kx. So the first term blows up as x goes to negative infinity. So as s goes to negative infinity, this term blows up, right? So we have to set a equal to 0 to prevent that. So if we set a equal to 0, the solution psi of x is equal to b times e to the kx. So first let's look at in the region where x, so let's start a new page. So psi of x equals b times e to the kx. So if in the region, so let's look at case number 1. So region x is greater than 0, so we have v of x is also equal to 0, right? So the solution, we have psi of x equals to b times e to the kx. This is when x is greater than 0. I mean it's less than 0. In the second scenario where x is greater than 0, we have the solution psi of x equals some constant, let's give it a name, f. f times e to the minus kx plus some constant g times e to the kx. But again, when x is greater, because this here is when x is greater than 0. So this term here blows up, right, at x equal to infinity. So we have to set g equal to 0, which leaves us with the solution psi of x equals f times e to the minus kx. Right, so now we have two solutions, this one and this one, for both regions where x is negative and one is when x is positive. So now in order to solve this equation, we have to look at the boundary conditions, right? So let's sum the solution here. So this is b e to the kx. This is if x is greater than or equal to 0. We have f e to the minus kx. This is if x is greater than or equal to 0. Alright, so in order to solve this, we have to look at the boundary conditions, and if you recall from earlier videos, we have two boundary conditions. The first one is psi is always continuous. 2 is the derivative of psi with respect to x is also continuous, except at the point where the potential is infinite. So the derivative of psi with respect to x is not continuous at v of x equal to infinity or when x equal to 0. This is the same thing, right? So looking at the first boundary condition, it tells us that f has to equal to b. So our solution psi of x is going to have to be equal to b to the b times e to the kx and b times e to the minus kx. This is x is less than or equal to 0. This is if x is greater than or equal to 0. This is what continuous means, right? So with this been said, if we just want to plot this function here, the psi function, we will get something like that. So this is our x coordinate. This is psi of x, and our wave function gonna look something like that, right? This point here is the square root of k, and this curve here is square root of k times e to the minus kx. Obviously there is a kick here where x is equal to 0, right? And remember, at this point we didn't say anything about the delta function. So at this point the delta function is not into the story yet. So let's look at the second boundary conditions where the derivative of psi must be equal to 0, but at x equals 0. So in order to look at this boundary condition, there is a trick. The trick is we have to integrate the Schrodinger equation. If you remember, it's minus h bar squared divided by 2m times the second derivative of psi with respect to x plus our potential function v of x times psi of x must equals to e times psi. So the idea is to integrate this equation from minus epsilon to positive epsilon. So if we integrate this dx to positive epsilon, same thing, we have to do it over here. So now the first integral, the first term, is nothing but d psi dx, right? Let's leave the second term as is. The last term here, this is dx, this is dx. Let's put the second term here. So the second term, we're gonna leave it as is. V of x times psi of x dx. This is gonna be equal to e times the integral of that psi dx. Alright, so now if we take the limit as epsilon approaches 0, if we take the limit here, we have to do it in each term, right? As epsilon approaches 0, let's do it over here. As epsilon approaches 0, this last term is equal to 0 as these two endpoints, epsilon from the right and the left, getting closer and closer to each other. So now let's rearrange few things. The first term is, we're gonna take the limit as epsilon approaches 0 of d psi dx, evaluating at positive epsilon, minus d psi dx, evaluating at the left of epsilon. This is equal to 2m divided by h bar square times the limit as epsilon approaches 0 of the integral from minus epsilon to positive epsilon v of x times psi of x dx. This left hand side by definition is delta d psi dx, right? Okay, so remember from earlier this video, we said, if you remember, what is our potential? It's minus alpha times the delta function of x. And if we evaluating this between around epsilon and taking the limit as epsilon approaching 0, this is the same as minus 2m divided by h bar squared. That's nothing new, this is this constant, times alpha, right, times psi of 0. It's gonna pick that value. This is from earlier this video. So now this is, we have this equation here. So now we're gonna plug this equation back into the solution. If you remember, the solution for psi, I can write it here, is b e to the minus kx. This is for x greater than 0, and then we have b or f, but remember from the first boundary condition we have b equals to f times e to the k x, where x is negative. So now if we take one derivative of psi, okay, what we gonna get? So d psi dx is gonna equal to minus b times k times e to the minus k x. And then the second, this is for x greater than 0, and then d psi dx is equal to b times k times e to the positive kx. This is when x is negative, right? So now let's look at d psi dx from the left and the right. So d psi dx from the right is going to equal to minus bk, and also d psi dx from the left is going to equal to positive bk, right? So now, since we have these two values, we can plug them back into this equation here, into this equation, this one right over here. So now let's get back here. So now we have delta d psi dx is equal to minus 2b times x, right? I mean times k. So times k. So since we know what k is, we defined it earlier this video, we can solve for k. So now k is equal to mass times alpha, which is joules times length, divided by h bar square. H bar is just joules second, okay? So yeah. Alright, so now that's that. So we can define the energy. The energy is equal to minus h bar square times k square divided by 2m. Or you can say E is equal to minus mass times alpha square divided by 2h bar square. So finally, let's normalize our wave function. So we're going to take the integral from negative infinity to infinity of psi star psi, or module square dx. So this, let's go to the next page. So this is equal to 2 times module square of b times the integral from 0 to infinity, that's where the 2 comes from, times e to the 2 minus 2k x dx. Finally integrating, we get absolute value, module square of b divided by k. This must equal to 1, and solving for b we get b equals square root of k, or b is equal to square root of m times alpha divided by h bar. So finally, now we have all the variables. So now the final solution, psi of x, for this wave function is square root of m times alpha divided by h bar times e to the minus m times alpha times absolute value of x divided by h bar square, with energy values equal to minus m times alpha square divided by 2 h bar square. There you have it. This is the solution for what? This is for the bound state, right? So what about this is for the bound state where the energy is negative. Energy is less than 0. In other ways, this is like, this is your potential V. This is what a bound state in the classical point of view, and you have your particle here, or a car, and it's trapped. It cannot escape this potential. That's what it means. So now we have to look at the scattering states, where the energy is positive, is greater than 0. So for the scattering states, our Schrodinger equation reads the second derivative of psi with respect to x equals to minus 2m times e divided by h bar square times psi, right? Or in terms of k, it's minus k square times psi, where k is defined as square root of 2m e divided by h bar. Remember now, e is positive, is greater than 0. So now this is the Schrodinger equation where x is negative. So this is x is negative and the energy is positive, is greater than 0. So the general solution for this one is psi of x equals a times e to the I k x plus b times e to the negative I k x. So here in this equation, this is the solution, but it has a lot of things missing in it. We have to find the a, we have to find the b, and we have to find the k. So this is not done. So similarly, this is when x is negative, x is less than 0. If x is greater than 0, our solution, psi of x, it's going to look similar but with different normalization constants. So this is f times e to the I k x plus g times e to the minus I k x. So now we have to invoke boundary conditions to find a, b, f, g, and k. We have 5 variables to look at. But the sad story is we only have 2 boundary conditions. The first boundary condition tells us that psi must be continuous everywhere, which means that f plus g is equal to b plus a. So that's equation, let's call it equation number 1. Okay, and the second boundary conditions tells us that the derivative of psi must also be continuous everywhere but at x equals 0. So let's look at this boundary conditions. This is a little bit more complicated. d psi dx equals to I times k times f e to the I k x minus g times e to the minus I k x, and also we have d psi dx is equal to I times k times a times e to the I k x minus b times e to the minus I k x. So this is from the right, and this is from the left. X equal to less than 0. So looking at the first one, d psi dx, from the right side, this equals to I k times f minus j. And then looking at d psi dx from the left, this is going to equal to I k times a minus b. Right? So now so let's look at the difference in the delta d psi dx, right? The same steps here, we're following the same steps. So that's going to equal to I k times the variables f minus g minus b minus a plus b. Here we go. And we also know that psi of 0 is going to equal to a plus b. So the second boundary conditions tell us that, gives us this equation, I times k times the variables f minus j minus a plus b must equal to minus 2 times mass times alpha divided by h bar square times a plus b. Let's call this equation number 2. Ooh, that's bad news. You know why? Because we have 2 equations and 4 unknowns. Ooh, no, 5 unknowns if you count k. So let's look here at, so this is equation number 1. okay, and here we have equation number 2, but we have the variables f, j, g, a, and b, also k. So 2 equations, 5 unknowns. This is bad news. So let's put this in more friendly form. Let's define the new variable beta. Beta is equal to mass times alpha divided by h bar square times k. So with this new variable, we have our equation f minus g equals a times 1 plus 2i beta minus b times 1 minus 2i beta. Alright, so now, since we can't really solve this mathematically, let's look at the physical reality. The physical reality, when we have these equations, when we have a beam of particles, this beam must come either from the left or from the right, right? So for a beam of particles scattering from the left, we have g must equal to 0. To explain this, let's plot a graph here. So this is x, this is the y coordinates, and this is our wave function here. It goes down, it comes back up. So coming from the left, we have this incident beam, okay? The incident wave is made out of a times e to the ikx. So this incident wave coming from the left is going to have the reflected wave. This reflected wave is the b1, b times e to the minus ik x, right? And we also have transmitted wave, and this is the f wave. It's going in that direction, to the right. So f times e to the I k x. So g, which supposedly coming from here, so let's put in different color. So this is the g wave. For a physical reality situation, it doesn't make sense that this wave gonna get reflected after this infinite barrier here. So this is e to the minus k x. So similarly works if the scattering coming from the right, then g must be the incident wave, f must be the reflected wave, b is the transmitted wave, and a is 0. So with this being said, we have these two equations. We have the b equation is equal to, so we're going to use equation number 1 and 2 to solve this. So this is going to equal to I times beta divided by I minus I beta times a. That's one equation. The second one is equal to f equals 1 divided by 1 minus I times b times beta times a. So up to this point we can't really solve this, okay, because we still have more variables than equations. But what we can do, we can find the relative probabilities. So the first relative probability is going to be for the incident wave, okay? So this is the probability that an incident particle will be reflected back. So this is r. We're going to define r as modulo square of b, that the reflected wave divided by the transmitted wave, the probability of the transmitted wave. So this here the reflection this is the reflection coefficient. So R is the reflection coefficient. Also, we have to find the transmission coefficient. As you can guess, the transmission coefficient, we're going to give it a letter T, and we're going to define it as the transmitted wave probability, the probability that the wave is being transmitted, divided by the incident wave square. So for the R1, so R is equal to module square of B, which we have, right, divided by module square of A, which is equal to beta square divided by 1 plus beta square, and T is equal to module square of F divided by module square of the incident wave. And if you do the math, we get 1 divided by 1 plus beta square. Finally, what common sense says that the transmitted wave and the reflected wave, these are probabilities, yeah? So the sum of these probabilities must equal to 1. So R plus T must equal to 1. So this is another equation here that's very, very useful. Okay, so let's put these R and T's into the original variables. So R is equal to 1 divided by 1 plus 2 h bar square times E divided by m alpha square, and then T, the transmitted wave, is equal to 1 divided by 1 plus mass times alpha squared divided by 2 h bar square times E. As you can see, for the higher the energy, the greater the probability of transmission, which certainly make a lot of sense, right? There's a mathematical miracle in here, okay? Because if we look at the problem from the beginning, so this is x, this is our potential function. Oof, let me fix it. This is our potential function, v of x, which is given by alpha times the delta functions, so, delta of x. So it's infinite at x equals 0, and it's 0 everywhere else. So this is x equals 0. So let's look at this problem classically, okay, using classical physics. Using classical physics, if the energy, okay, is greater than the maximum potential energy, V max, okay, then T, the transmission coefficient, is equal to 1. This is very obvious, right? And R is equal to 0. So, you know, you have some potential energy here. Okay, so this is, let's say, V max, and the energy coming from the left is greater than this. It's just gonna pass through it. There's no way it's gonna reflect. Similarly, if this is classically, if E is greater than less than V max, which means this, let's say, the energy coming from here, so this is E, it's gonna hit this potential barrier, okay, and most certainly T is gonna equal to 0, and the reflection coefficient must equal to 1. But however, with the quantum mechanics, okay, there's a phenomena called tunneling, and here we have our potential function. Even if the potential function is infinite. In this case it is for the delta function. So let's say this is V max, and the energy coming from the left is greater than V max. You would assume this is the energy. You would think that the transmission coefficient is equal to 1 and the reflection coefficient is equal to 0, because the energy is greater than this potential energy, so it's just gonna pass through it. But this is actually not true. There is a chance that R is greater than 0. There is a probability that this energy gonna reflect back. So it's just gonna go through here. As soon as it feels this potential, it's just gonna reflect back. There's a probability, and this probability depends on alpha square. Okay, so this probability depends on this variable alpha square. The same way goes if the energy is less than V max. So this is our energy. So if the energy is less than V max, using the phenomena of tunneling, there's a chance that this energy, this wave gonna come here and tunnel through this and pass through it. So T, transmission coefficient, there's a chance it's gonna be greater than 0, and that's also depend on alpha square.